In the last class, we discussed some problems by using the torsion equation. And in this class, I'm going to discuss the concept of shafts connected in series and parallel. So if the shafts of same or different cross sections are connected end to end and subjected to a torque is said to be shafts in series. Whenever we connected the shafts end to end, then the shafts are said to be in series. In this concept, there are three cases to be studied based on the application of torque position. Where the torque we are going to apply on the shaft, based on that, we are going to study three cases. First case one is torque is applied at one end and one end is fixed. Second one is torque is applied at two or more points. Third case is torque is applied at common point or junction. These are the three cases in which we are going to solve the problems. Let us go for the case one. Torque is applied at one end. When we applied the torque at one of the end. So let us look this diagram. This diagram shows that the shaft, two shafts are there which are having different cross sections and which are connected end to end like this, and one end of the shaft is fixed and another end of this shaft is applying a torque, clockwise torque. When looking from the right side, it is T is the torque, and A, B, C are the points of end points of the shafts. D1, D2 are the diameters, and L1, L2 are the lengths. At different lengths and different diameters, shafts are connected in series by applying the torque at one end. What is the stresses which will be developed in the shaft? This is the first case. Let us draw the free body diagram for that. Consider two shafts AB and BC. So AB is the one of the shaft which having the length L1 and the diameter D1, and BC is the portion of the shaft which having length L2 and diameter D2. Okay, of different cross sections are connected together in series with a torque is applied at one end and another end is fixed. The shaft is fixed at A and torque is applying at point C. In this case, both the shafts are subjected to same torque, which is equal to applied torque. That means when we apply the torque at one point at the end of the shaft, this torque is applied on the BC and also the torque is applied on the AB. It will understand by drawing the free body diagram of this given problem. The same relative reactive torque is developed at the fixed rate. When we applying the torque at this point, clockwise torque when looking from the right side, the reactive torque will be developed in opposite direction at point A. Anti-clockwise torque will be developed, reactive torque at point A. Here, in opposite direction to the applied torque. So free body diagram for the given diagram is, free body diagram means if we draw the individually separately from separately at the body, first body AB and second body BC. Okay, so if you draw the member AB and BC separately, so this is the torque which we are applying at points in clockwise. To maintain this BC member in equilibrium, there must be a opposite direction, opposite torque will be developed at point B. Same amount and opposite torque will be developed at the point B. So if we apply the torque in clockwise, then an anti-clockwise torque will be developed at point B to maintain the BC member is in equilibrium. Clear? So opposite torque T, and let us take the member AB, shaft AB. The reactive torque will be developed at a point A in opposite direction, anti-clockwise direction, opposite to the torque which we are applying at point C. Same amount T. To maintain this AB member is in equilibrium, the opposite torque will be developed again. A clockwise torque will be developed at point B. T. T is the torque. So when we are joining these two members again, it is in anti-clockwise torque, and it is clockwise torque will be cancelled, and there is no torque will be applied at point B when we are joining these AB and BC together. Clear? So like this, we have to draw the free body diagram before going to solve the problems. Then only we can know the torque, individual torque, we can the torque which you are applying on the individual members. Okay, clearly. So now these two members are subjected to same torque T. That is clockwise torque when we looking from the right hand side of the shafts. Okay. Therefore, these two torques are therefore these two members are rotated clockwise direction when we looking from right hand side. This is the free body diagram. The free body diagram ela draw cheyalo. Free body diagram means we are drawing individually, the separately shafts are AB and BC, and we are providing a torque separately in two members. Okay. So total angle of twist is sum of the individual angle of twist in both the shafts. When we calculating the angle of twist in both shafts, this is rotating in clockwise direction when we are looking from the right side, and it is also rotating clockwise when we are looking from right side. Therefore, both are the same in the same direction. So total angle of twist is equal to sum of the angle of twist in each shafts. Let us find the angle of twist in first shaft. Angle of twist in AB. Angle of twist in AB, which having the length L1 and diameter D1. Applied torque is T. So let theta 1 is the angle of twist in AB. From the torsion equation, we know that torsion equation is the G theta by L equal to T by J. From this torsion equation, G1 theta 1 by L1 is equal to T by J. G1 theta 1 by L1 equal to T by J1. T is the torque applying on the shaft, which is same in both the shafts. On both the shafts, we should not write T1 T2 because T is the same on both shafts. So here we are looking, T is applying at point C, and also T is developed at the point B in same direction. That's why I'm writing only T. Therefore, theta 1 is equal to TL1 by G1 J1. Here T is the torque, L1 is the length of the shaft, G1 is the rigidity modulus for the shaft material 1, and J1 is the polar moment of inertia of shaft 1. Similarly, angle of twist in BC. Angle of twist in BC portion, let theta 2 is the angle of twist in BC. From the same torsion equation, we can write as G2 theta 2 by L2 is equal to T by J2. From this, theta 2 is equal to TL2 by G2 J2. From these two equations, we can write the total angle of twist is theta 1 plus theta 2. Both are in same direction. That's why I'm summing up these two, theta 1 plus theta 2. So we can write this equation as T is the same for both the shafts. We can take it as common. T into L1 by G1 J1 plus L2 by G2 J2. If the shafts are made with the same material, then G is also same for both the shafts. So we can take it as G is also common. T by G equal into L1 by J1 plus L2 by J2. Since G1 equal to G2 equal to G. If the shafts are made with the same material, if these two shafts are made with the same material, then their rigidity modulus are same. So finally, you can calculate the total angle of twist by using this equation. Clear, students? Therefore, shear stress in AB. How to calculate the shear stress in AB? How much stresses will be developed in AB? From the same torsion equation, let T1 is the shear stress in AB. From the same torsion equation, another two parameters, τ by R equal to T by J. By applying this equation for the first shaft, that is the portion AB, τ1 by R1 equal to T by J1. T is the same for both the shafts. τ1 equal to T by J1 into R1. Otherwise, τ1 equal to T by, what is the formula for polar moment of inertia? Pi by 32 d1 power 4, diameter power 4 into R1 is half of the first diameter, d1 by 2. Upon simplifying this expression, we can write that expression as τ1 equal to 16T by pi d1 cube. This is the formula to calculate the shear stress in first shaft, 16T by pi d1 cube. If you know the torque and diameter, then we can calculate the shear stress. Similarly, shear stress in BC. In second portion of the shaft is τ2 is equal to 16T by pi into, in place of d1, we can write d2. So pi d2 cube, 16T by pi d2 cube is the shear stress in second portion of the shaft, that is BC portion. Clear, students? Like this, you have to calculate the angle of twist and shear stress in each shaft when the shafts are connected in series, and the torque is applied at one point and another point is fixed. This is the first case. Clear, students? Like this, you have to find in first case. Let us look the problem on the first case. First example, worked example, example 10. Up to 9th example, we solved the problems in previous concepts. Then example 10, let us read the problem first. A shaft shown in figure is fixed at one end at A and is subjected to a torque of 8 kilonewton meter. 8 kilonewton meter, which is applying at end C, shown in diagram. Find the maximum shear stress and total angle of twist in shaft. Take G equal to 80 GPa. This is the rigidity modulus for both the material. Both are made from same material. That's why we are taking G as 80 GPa for both AB and BC. Torque is 8 kilonewton meter, 8000 Newton meter. G is 80 GPa, 80 into 10 to the power of 9. G is the giga. Giga means 10 to the power of 9 newtons per meter square. We have to find the maximum shear stress in the shaft and total angle of twist. Before going to calculate the maximum shear stress, where should the maximum shear stress will be developed out of these two shafts? Either is it AB or in BC. In which portion of the shaft the maximum shear stress will be developed? How to identify that maximum shear stress? The shear stress formula already we written that shear stress formula is 16T by pi d1 cube. So maximum shear stress will be developed in the shaft for which the diameter is smaller. When the diameter is smaller, the shear stress is maximum. These are inversely proportional. Tau is inversely proportional to d1 cube. So diameter takkoga unte shear stress will be maximum. So from that concept, we can say that the shear stress which will be developed in portion BC is maximum and more than the shear stress developed in the portion AB. Clear? So maximum shear stress will be developed in the member BC because portion BC having less diameter than the AB. So portion BC lo ఎక్కువ stress develop అవుతుంది because it's having less diameter than the AB portion. Therefore, maximum shear stress in BC. So maximum toe max is equal to, from the similar formula which are derived in the previous section here, toe 1 is equal to 16T by pi d1 cube. We have to calculate the maximum shear stress from this equation. So maximum toe max is equal to 16T divided by pi into diameter of the portion BC cubed. 16T by pi dBc cube. dBc means diameter of the BC portion. Okay. So maximum stress toe max is equal to 16 into T is the 8,000 newtons. Torque developed on this shaft is 8,000 Newton meter divided by pi into diameter of the portion BC is 90 mm is given. 590 means diameter 90. 500 is 100 mm diameter for the portion AB. So we are calculating the shear stress in BC portion. That's why we are taking diameter of the BC. So 90 mm is given. If it is converted into meters, 90 by 1000, then 0.09 cube is the diameter cube. Therefore, we will get 55.88 into 10 power 6 newtons per meter square. This is the shear stress units comes from this formula in newtons per meter square. So 10 to the power of 6 is mega, newtons per meter square is Pascal. Therefore, we can replace this 10 to the power of 6 newtons per meter square by megapascal. So 55.88 megapascals. So maximum shear stress will be developed in BC portion is 55.88 megapascals. Clear? Then angle of twist, total angle of twist. Already we written this formula from the previous equation. Theta is equal to T by G into LAB by JAB plus LBC by JBC. These are the length of the portion AB, polar moment of inertia of AB, and length of the BC, polar moment of inertia of the BC. T and G are the same for both the portion. So theta is equal to T by G into LAB by pi by 32 DAB whole power 4. This is the polar moment of inertia formula. Pi by 32 d power 4 is the formula for the solid shaft. So here I am taking the diameter of the AB portion, and here I am taking diameter of the BC portion. So 32 pi by 32 is the common from the both expressions. So therefore we can write in the out of the bracket 32T by pi G it becomes into LAB by DAB whole power 4 plus LBC by DBC by whole power 4. 32T, T is the 8,000 Newton meter is given in the problem by pi into G value is 80 GPa, 80 into 10 to the power of 9 into LAB, portion AB. Portion AB is the length having the 1.5 meters and portion B having the length 2.5 meters. So 1.5 divided by 0.1 is the diameter of the AB portion, 100 mm. So 0.1 power 4 plus 2.5 length of the second portion BC divided by 0.09 power 4. Upon calculation of this equation, we can get theta is in radians. That is theta equal to 0.0454 radians. So if we convert this radians into degrees, we will get theta as theta of 3.09 degrees. Theta value as 3.09 degrees. How to convert the radians into degrees? If we multiply this value by 180 and divided by pi, then we will get in degrees, 3.09 degrees. Okay, total angle of twist of the shaft is 3.09 degrees in clockwise when we are applying the torque 8,000 Newton meter at the end of the shaft. Clear? So let us go for the second case. Torque is applied at 2 or more points. Look at this diagram. Dear students, we are applying the torque at 2 points on the shaft, and by fixing one end is fixed at A, and we are applying the torque at point C and also at the junction point B. We are applying T1 is the torque at C in clockwise direction when looking from the right side, and it's the anti-clockwise direction T2 at point B when we're looking from right hand side. So this is a clockwise couple, a clockwise torque, and this is the anti-clockwise torque which are applying at different points of the shafts. Okay, this is the second case. How to solve this second case? Consider a shaft consisting of two cross sections and is subjected to torque at 2 points as shown in figure. In this case, the shafts are subjected to different torques individually, and the total angle of twist is algebraic summation of individual angle of twist. Okay, let us draw the free body diagram. For that, while we are drawing the free body diagram, what is the torque developed in each shaft we should know. So when we drawing the free body diagram for the portion BC, on which at C point there is a torque T1 which is applying at point C in clockwise direction. T1 is applying at point C clockwise direction. We are looking from right hand side. So to maintain the portion BC is in equilibrium, there must be a opposite equal torque will be developed at point B. If we apply the clockwise torque at C, there will be anti-clockwise torque will be developed at B, T1. Otherwise, when we are applying the anti-clockwise torque at point C, there is a clockwise torque will be developed at point B. Okay? Equal and opposite torque will be developed at another end to maintain that shaft is in equilibrium. Otherwise, if we apply the torque T1 at one end, that will be rotated without any torque. This torque will be not developed at the point B, this shaft will be rotated simply. It will not develop any twisting movement or transmit the power from one end to another end. To transmit the power or to maintain the equilibrium of the shaft, when we are applying the torque at one end, there will be a opposite, equal and opposite torque will be developed at the other end. Then only that shaft must be maintained in equilibrium. Okay? So T1 is in opposite direction, opposite anti-clockwise direction at point B. If we connect these two, there will be another torque T2. There will be another torque in anti-clockwise direction T2 at point B. Therefore, if we connect these two, there must be a T2 in anti-clockwise direction. Therefore, here T1 is a clockwise direction, T2 is in anti-clockwise direction. Resulting of these two means T1 clockwise, T2 anti-clockwise. Therefore, resulting of these two is T1 minus T2 in clockwise. T1 minus T2 in clockwise torque, resulting torque. There will be a reactive torque at point A will be developed. At A reactive torque will be developed. A reactive torque must be equal to the resultant of these two. So T1, T2 is in clockwise, a reactive torque is in anti-clockwise. There will be a T1 minus T2 anti-clockwise torque will be developed at point A. So T1 minus T2 in anti-clockwise direction. To maintain this portion AB is in equilibrium, there must be a T1 minus T2 torque will be developed in clockwise direction at point B. If you join these portion again, this is the anti-clockwise T1, that is minus T1. This is clockwise T1 minus T2. If you add these two, T1 cancel. Minus T2 is in anti-clockwise direction. Minus T2 is in clockwise direction. Therefore, minus T2 in clockwise. Therefore, T2 is anti-clockwise direction. Torque will be developed. Again, we will get a same diagram. Clockwise, anti-clockwise direction T2. మళ్ళీ రెండు జాయిన్ చేస్తే ఏంటంటే యాంటీ-క్లాక్వైజ్ డైరెక్షన్ లో T2 రావాలి. సో ఎలా వస్తుంది ఇది ఒక్కసారి అబ్జర్వ్ చేయండి. ఇది ఇక్కడేమో యాంటీ-క్లాక్వైజ్ డైరెక్షన్ లో T1 డెవలప్ అవుతుంది. ఓకే, పాయింట్ B దగ్గర. ఇక్కడేమో క్లాక్ వైజ్ డైరెక్షన్ లో T1 minus T2. T1 minus T2. Okay. If you write this anti-clockwise torque in clockwise torque, then we will replace that T1 by minus T1. If you add these two, there will be a clockwise couple or clockwise movement. T1 minus T2 minus T1, T1 cancel, minus T2 is there, minus T2 torque will be developed in clockwise. So if it is mentioned in clockwise, anti-clockwise direction, minus T2 replaced by plus T2. So there will be anti-clockwise direction, clock will be developed at point B, T2 value. Okay, therefore we will get the same diagram as mentioned in the Prof. Okay, so therefore finally T1 is torque will develop on the shaft BC, and T1 minus T2 will be developed on the A. There are two different torques will be developed in two different shafts. Note, if T1 is greater than T2, if T1 is greater than T2, T1 T2 కంటే ఎక్కువగా ఉంది అనుకోండి, ఇటువైపు యాంటీ క్లాక్ వైజ్ రొటేషన్ ఎక్కువ జరుగుతుంది. T2 అనేది తక్కువగా ఉన్నప్పుడు క్లాక్ వైజ్ రొటేషన్ ఎక్కువ జరుగుతుంది. అంటే BC పోర్షన్ rotates clockwise, AB portion rotates anti-clockwise. Okay, so theta, total angle of twist is theta BC plus theta AB. Theta BC means angle of twist in portion BC plus angle of twist in portion AB. If T1 is greater than T2, T1 ఎక్కువగా ఉంది అనుకోండి, ఇది clockwise rotate అవుతుంది. T1 ఎక్కువగా ఉన్నప్పుడు ఇది కూడా clockwise direction లో rotate అవుతుంది. T1 ఎక్కువగా ఉంది అనుకోండి, for example T1 is 10, T2 is 8 Newton meter, then 2 kilonewton meter will be clockwise. Therefore it is in clockwise rotation, it is also clockwise rotation, both are in same direction. Therefore we can take positive sign to calculate the total angle of twist. Total angle of twist theta is equal to angle of twist in BC portion plus angle of twist in AB portion. If T1 is less than T2, if T1 is less than T2, this is already in clockwise direction, T1 anti-clockwise rotation, and T1 is less than T2. If T1 less than T2, it becomes negative. If T1 is less than T2, T1 minus T2 is negative. Negative in clockwise means positive in anti-clockwise. Positive in anti. This portion AB will be rotated in anti-clockwise direction. This is the portion BC is rotated in clockwise direction. Both are theta AB, theta BC is in clockwise, theta AB is in anti-clockwise. Therefore, total angle of twist is theta BC minus theta AB. Okay, like this you have to take. Subtract that angle of twist from BC to AB if the torque T1 is less than T2. If T1 is equal to T2, if we apply the torque at end point and junction are equal, if T1 is equal to T2, it will be rotated in clockwise direction by the T1. If T1 is equal to T2, this is 0. There is no torque developed in the BC. T1 is equal to T2, then torque developed on the portion AB is 0. Therefore, if we calculate the total angle of twist, the angle of twist BC itself, total angle of twist is equal to angle of twist in BC itself. The angle of twist in AB is 0 because there is no torque applied on the AB if T1 is equal to T2. Therefore, theta is equal to theta BC. These are the three expressions in this case. If T1 is greater than T2, if T1 is less than T2, if T1 is equal to T2. Clear? This is the second case. Torque is applied at 2 or more points. Let us look the one problem in this class. On this case, a solid steel shaft 2.4 meters long of uniform circular section is fixed at one end. It is the total diameter is same, uniform circular section is fixed at one end and is subjected to clockwise torque 800 Newton meter at the free end. Free end దగ్గర 800 Newton meter clockwise torque apply అవుతుంది and counter clockwise torque, anti-clockwise torque of 400 Newton meter at 1.6 meter from the fixed end. ఇక్కడ నుండి 1.6 మీటర్ డిస్టెన్స్ లో యాంటీ క్లాక్ వైజ్ టార్క్ డెవలప్ అవుతుంది. దట్ ఈస్ 400 న్యూటన్ మీటర్. Let us take this is the T1 and T2. From the fixed end, determine the required diameter if the angle of twist is not to exceed 3 degrees. ఎంత డయామీటర్ యూజ్ చేస్తే దీనికి యాంగిల్ ఆఫ్ ట్విస్ట్ 3 degrees కంటే ఎక్సీడ్ అవ్వకుండా ఉంటుంది. దట్ ఈస్ ద క్వశ్చన్. ఓకే, ఇది మనం అప్లై చేసినప్పుడు దీస్ టూ టార్క్స్ ఏ యాంగిల్ ఆఫ్ ట్విస్ట్ ఇన్ దిస్ షాఫ్ట్ మస్ట్ బి విత్ ఇన్ ద లిమిట్ ఆఫ్ 3 degrees. So what is the diameter should be maintained? Take G is equal to 83 GPa, 83 gigapascals. So the diameter ఎంత మెయింటైన్ చేస్తే యాంగిల్ ఆఫ్ ట్విస్ట్ 3 degrees కంటే ఎక్సీడ్ అవ్వకుండా ఉంటుంది, లిమిట్ దాటకుండా ఉంటుంది. Okay, so let us do this diagram. This is the shaft. Orange color is the shaft. A, B, C is the shaft. That shaft is fixed at A and torque is applied at point B and C. At C free end a clockwise torque 800 Newton meter, at B 400 Newton meter anti-clockwise torque when looking from the right hand side. Okay, L to L1 as the length of these two portions BC and AB, and diameter is the same throughout the section. Let us draw the free body diagram for this. If you draw the free body diagram for the portion AB and BC, both are having the same diameter D, and portion BC, there will be a T1 will be developing at a point C in clockwise direction, and you should draw the anti-clockwise torque at T1 at point B, same amount of T1 torque and opposite direction to maintain the BC portion in equilibrium. And if you draw the free body diagram for the AB portion, there will be a T1 minus T2 resultant of these two. A reactive torque will be developed at point A, T1 minus T2 in anti-clockwise direction. Therefore, to maintain the AB portion in equilibrium, the equal and opposite torque will be developed at point B, T1 minus T2 in clockwise direction. Okay, this is in clockwise direction at C and anti-clockwise direction at P in portion BC. And the clockwise torque will be developed at point B in portion AB, and anti-clockwise torque will be developed at point A in portion AB. This is the free body diagram. Length of the AB is 1.6 meters from the fixed end to B, and the remaining length, total 2.4 meters length, the remaining length is the BC is 0.8 meters. Okay, so in this problem, we are going to find the required diameter should be maintained for both the shafts. So portion BC and portion AB, separately we are calculating the angle of twist in portion BC. So angle of twist in portion BC, to calculate the angle of twist, we should take that torsion equation G theta by L equal to T by J is the formula, basic formula. By applying that formula for the portion BC, let us take the portion BC as member 1, portion BC as member 1, and portion AB as member 2. Okay, for the member 1 portion BC, G into theta 1 by L1 equal to T1 by J. So J is same and G is same for both the shafts, both the portions, because the G is the material property which is same throughout the length, and J is the polar moment of inertia. The diameter is the uniform, therefore J is also same for both the section, both the portions. So from this equation, theta 1 is equal to T1, that is the torque applied on the portion BC divided into L1 divided by G into J. So T1 is the torque applied on the portion BC. How much torque applied in the portion BC? T1. What is the T1 value? Your T1 value is 800 Newton meter. 800 Newton meter. So 800 into length of the portion BC is 0.8 meters divided by 83 into 10 to the power of 9. 83 is the Young's resistivity modulus for the material. 83 into 10 to the power of 9 into pi by 32 d power 4, diameter power 4. Finally, the angle of twist in BC theta 1 in terms of diameter, 7.85 to 10 to the power of minus 8 by d power 4. Similarly, we can calculate the portion AB, angle of twist in portion AB, G theta 2 by L2 equal to T2 by J. Theta 2 equal to T2 L2 by GJ. So T2 is what is the T2 value? Here T2, what is the T2? T2 means the torque applied in the portion A. Torque applied in the portion AB is T1 minus T2. How much T1? T1 minus T2, 800 minus 400. 800 minus 400 is 400. So torque applied in the second shaft is 400. Okay. T2 means it is torque applying on the second shaft. Torque applying on the second shaft is in this case T1 minus T2, 800 minus 400 is 400. Clear? So 400 Newton meter into length of the portion AB is 1.6 meters divided by G value is 83 into 10 to the power of 9 into pi by 32 D power 4 again. D is the same for the shaft AB also. So theta 2 is equal to, upon calculation of these values, we will get the same value as that of the first case, 7.85 into 10 to the power minus 8 D power 4 itself. So theta 1, theta 2 are same. Therefore, total angle of twist is equal to theta 1 plus theta 2. Since T1 is greater than T2. Whenever T1 is greater than T2, both shafts rotating in clockwise direction. That's why we are taking positive side. We have to summing up these two angle of twist, theta 1 plus theta 2. Therefore, theta is equal to 7.85 into 10 to the power minus 8 by D power 4 plus 7.85 into 10 to the power minus 8 D power 4. Both are same. So theta is equal to 2 times 2t, 2 into 7.85 into 10 to the power minus 8 D power 4. So this is the total angle of twist in terms of diameter. Already in the problem, the angle of twist is given. Total angle of twist is not to exceed 3 degrees. So theta value is 3 degrees given. Also theta is equal to 3 degrees means 3 into pi by 180 radians. This is 0.0523 radians. Therefore, from these two expressions, 0.0523 is equal to, this theta is 0.0523 is equal to 2 into 7.85 into 10 to the power minus 8 divided by D power 4. From this expression, we can write D power 4 as 2 into 7.85 into 10 to the power minus 8 divided by 0.0523. D power 4 equal to 3 into 10 to the power minus 6, D equal to 0.0416 meters. This is the diameter of the shaft in meters, or required diameter of the shaft D is equal to 41.6 mm. Clear? This is the required diameter should be maintained to avoid to exceed the angle of twist 3 degrees. Clear, students? Like this you have to calculate by taking the free body diagram of the given problem. After drawing the free body diagram, how much torque will be applying in both the portion, based on those torques, we can calculate the angle of twist. By using that angle of twist, we can calculate the required diameter of the shaft. Okay. Up to this point, I'm closing this class. In the next class, I will discuss remaining problems on that is case 2, and also I will discuss a remaining case. That is, the remaining case is torque is applied at a common point by fixing both the ends. This is the third case in the shafts in series. I will discuss this concept in the next class. Okay, students, I will close this class. Have a nice day. Bye.